So this is a fundamental topic that I wanted to dive into because a lot of what awaits us is going to be based on it. And we've hinted at this a little bit as we started talking about relational database management systems. We said that part of the power of a relational database system is that it gives you all this crazy ability to report in ways that you never imagined, years and years later. In fact, the biggest thing when you're designing a database, as we'll see, is really to kind of try to capture all the data points that you will need for future growth and for future queries, and because you can use the versatility of that high level language we called SQL to gain insight into your data in ways that you just never even imagined when you built it, right? And that part is pretty much baked in. As you'll see, this is extremely flexible. What you have to be really careful about is when you're designing is that you actually capture all the data so that you can query anyway. But what we want to talk about now is relational algebra. We want to talk about the mechanism that allows our high-level functional language SQL to yield the power that it does. This is a formal language. It is the platform on which SQL, which is implemented on it, works. In a weird abstract way, you can kind of think of it as like more of an interpreter than a compiler, but you can think about it as the engine on which SQL runs. Once you understand the relational algebra that's working at the lower level, so to speak, and really SQL is just being interpreted into it, then you can kind of understand better as we start getting into talking about how to join relations and how to actually decide what attributes to put in a relation and keys and functional dependencies and all these pieces. As we start to look at them, you'll see that you can define all of this using relational algebra. So this is a very core concept to how relational databases work. And I will go through, and as I go through this, I should say, I will point out kind of the SQL bits and pieces that you're using on top that represent these things. So for example, when we talk about renaming, right? So when you have a select query and you want to rename an attribute to be something else, anybody who's seen a select query before, this might sound familiar. You might list the attribute and then have as and another name. Again, this is implementation specific, so I'm going to go for a pretty generic approach. That is a representation of something that we're going to talk about as a rename operation. Okay, so as we do these, I'm going to try to point out the SQL that you will get to know them as, because you won't be writing in relational algebra, you'll be writing in SQL, but you'll be using relational algebra. So the reason I want to do that now, because you haven't formally been introduced to like select statements and joins and the kind of stuff that I'm going to be talking about, is because some of you may or may not have seen it before, and having that exposure and then going through this content and being able to relate it back to that is going to be very powerful for those of you who have been lucky enough to have been exposed in the past. That will help connect the dots, I think, a lot faster than anything else. And honestly, for those of you who have never seen a lick of SQL before, I'm not going to do it in such a way that you won't be able to like progress, because it's just going to be an add-on. It's going to be like, okay, we talked about the relational algebra, now this is the SQL that you might see it as, but it will help enforce what SQL looks like. So you keep seeing it bit by bit by bit, so then when we do see it, it'll make it easier to digest because it won't be the first time. And then you'll be able to come back to this as we do that and kind of review, like, okay, we're talking about joins now. I remember Brian was saying, something about that here with, sets and theta. Oh, okay, here it is, right? So hopefully that will help and you'll be able to kind of put it all together that way too. So that's something like the book doesn't do. So like and please do read through this chapter in the book. It's very important. This kind of content, by the way, this is stuff that, as much as I would like to be like, hey, I'm the database guy, and I know everything about databases. Relational databases have been around for a long time, right? This is very established stuff. Courses like this, I teach two types of courses. I teach courses that are a little bit more on the edge, as far as they might be more software engineering, and they might be more kind of just out on the bleeding edge of we're using functional programming, and we're doing these project-based things, and there really isn't very good books for that. Some courses are a hybrid, like I teach robotics, and robotics I get to kind of hybrid approach that one, because there are a lot of good books with robotics. But things like this is very, like, I'm not going to come up with a custom curriculum that is going to outshine the established good books, right? So that is why I'm usually not that kind of teacher that is very like follow the book and that kind of thing. But in this case, I think if I wasn't doing that, I wouldn't be doing this course justice. So please do follow along with the book. It is important. You'll see as I go through the slides, I on purpose try to add to what the book gives you, and I try to then help bring the pieces together. But I also try, almost always, not all the time, to follow along with where the book is, so that you can do that too and very easily see where these slides relate to that content. All right, so that aside, behind us, let's talk a little bit more about relational algebra. So there's going to be, especially as we start this, what we're really focusing on here, the high level, is that we're going to be taking a simple set of operators, all right? And we're going to be using them to operate on relations and produce a relation as a result. So remember that our relations are our tables, and we're going to be using these operators to operate on those tables, and they will be giving us back a table as a result. So that is kind of like the high level of what we're doing with relational algebra. Now we're going to categorize these operations into, that should be four, not fall, to four broad categories. Set operations, and we'll talk about those in a moment. Hopefully you've seen set operations in math, but we're not going to be, this isn't another math course, and I am going to bring these up again, union, intersection, and difference, in case you're a little bit rusty. This is not hard, so that part should be fine. Then we're also going to talk about operations that remove parts of a relationship. So there's going to be these two, selection or projection, that remove, and then we're going to talk about operations separately that actually combine tuples from relations. But let's focus first on the removal. So remember that a relation is two-dimensional, right? So you have your tuples, which are the rows, and you have your attributes, which are the columns. And when we talked about relational databases, I had one slide where I had, like a spreadsheet looking grid, and there was a colored line representing a tuple and a colored line representing an attribute. And remember, the intersection of those two things is your value, right? That's your component. And what we're doing here is we're looking at each one of those dimensions, and we're going to have an operator to remove one of those dimensions either way. So our selection operator is going to remove tuples or rows. Our projection operator is going to remove columns. So now we can take our original relation and make it smaller. The other side of this is we're also going to have operators that combine tuples from two different relations. So this is where we're going to start talking about the idea of a product, which is basically a multiplication. We'll see that in a moment. And a join. And a join is maybe a little bit more strategic, and we'll talk a little bit more about that. There might be a way that we want to constrain how we bring these relations together. The last one we're going to look at is pretty simple, and that one is just how to rename. And that might sound almost kind of like tagged on the end, but if you've happened to have worked with SQL before, particularly with joins, you might know that anytime you're joining on similar attributes, you will have a situation now where you have a returned relation with multiple versions of that same attribute. So renaming comes into play when you don't want to have to reference by original table name dot and the attribute name. You can now say rename those things and make your life a little bit easier. So it does tie in with the one before it. So let's start with sets. So again, this is pretty fundamental. I just want to make sure we go through it quickly because it might not be something that is right up there in your frame of mind at the moment. So let's get it there. So if we have two relations, R and S, and I just picked those because again I'm using these examples from the book and it uses those, and they're not meant to imply that there's anything special about R and S. It's just like any other variable that you named in a programming language, right? We're just representing them with R and S. Later, I think we represent some with U and V, right? So just keep that clear as far as which ones we're working with, so that doesn't get confusing. If we have a union of these two things, all we're saying is that the tuples that are in R and the tuples that are in S, the resulting set that we create is going to have both. And it's not going to have a repeat, by the way, of what's in R and what's in S. If they have the same tuples, if the same rows exist in both, then we're not going to duplicate those rows. Okay, this isn't the attribute piece where we were talking about joins, and we're going to talk more in depth about. This is now we're talking about set operations, and we're talking about the tuples in them. So I'm going to give examples. I just want to talk about the definitions first. The intersection is now just where we have the tuples that are in both R and S, right? So if it's only in R, only in S, we don't care. Those are thrown away for an intersection. A set difference is now if we have, say, R minus S, we have the whole set of R, but not what is also in S, right? So the intersection part of R and S does not get returned as part of R in this case. That is the set difference. So let's see some examples here. So these relations are taken right from the book. It's our good old movie star relation. And we have Carrie Fisher, Mark Hamill in one, and then in the other one we have Carrie Fisher and Harrison Ford. So R and S. Now note that Carrie Fisher is in both, right? So that's obvious going to show up in our intersection. You can see down there it does. If we look at the union, which remember is the combination of these two things, the whole enchilada, we have Carrie Fisher once, not twice, Mark Hamill and Harrison Ford. Our intersection is just Carrie Fisher because she's the only one in both. And then our difference, remember, is R minus S. So you take R, you subtract S, which means we take out Carrie Fisher, and Harrison Ford is in S, right? We're not looking at S other than to subtract from R. Remember, you're subtracting the intersection, right, is actually what you're doing. So what is left is Mark Hamill, right, because it was R minus S. If it was the reverse, if it was S minus R, then what would be left was Harrison Ford. But in this case, it's Mark Hamill. So that is it really for that piece, right? Now we're going to get more into, we're beyond the basic set logic just to make sure we have a level set. And now we're going to get into the operations that are going to kind of whittle down our relation, right? We talked about those first before we get into joins. So we have projection here first. So what projection is going to do for us again now, remember, is create a subset of relations attributes. So here we're saying, if you imagine you have your select, right? For those of you who have seen SQL, if you have a statement like select name and city, well, it would be an and, it would be name comma city from user, what you're saying is, I want these two attributes, right? I don't want all the other attributes, like there might be zip code and email and all other kinds of stuff. I don't care about those in this particular projection. I only care about name and address, right? So that is what a projection is. We're creating a subset of attributes. So we're not going to return the whole relation here. We're only going to return the ones that mattered. When we use this, we denote it with the pi symbol. Remember, this is just the Greek alphabet letter pi. It doesn't denote 3.14, 156, blah, 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 159, whatever it is. It just denotes that we're talking about a projection. So I'm going to show you an example in a moment. We're saying here that we're choosing the columns, which again, remember, is analogous with our attributes, that we're going to return in our query. So if we had the same relation here that we worked with earlier, not the movie star one now, but the actual movies itself, if we did a projection of title, year, and length, this would come back like this. Now, this is not the SQL syntax. Again, this is the relational algebra. The SQL would be select title, year, and length from movies, right? That would be the SQL. This is the relational algebra that is underneath the SQL. So remember, I said SQL is literally interpreted, so you can kind of imagine what the interpreter is doing now. The interpreter is literally interpreting it into this relational algebra. Now, how it implements that is up to the implementation of that particular database management system, but that is the idea, right? That is what SQL sits on top of. So this is just simply taking the original relation and in this case returning those three attributes, and you can put whatever attributes there that you want. That's a projection. Now a selection, remember, is now we want to select which tuples or rows we want a subset of. So we have a relation and we don't want all of the rows back. We only want some of them. This is analogous to, for those of you who have used SQL, let's say we have a user table, and I want to return only the users with a first name of Brian. So I say, select, let's just say star, because I'm not doing a projection here. So I'm going to return star, just means I'm going to return all of the attributes. Select star from users, where first name equals Brian, right? So in that case, assuming that my attribute where my first name is stored is named first name, and that there's ones there with Brian, and forgetting about nulls and all that other stuff for a moment, that is now going to return just the rows that have Brian. So if there's 5 Brians in there, I'm going to get 5 tuples back, or 5 rows, right? So that's what this is. You can kind of think of this as the where clause for now in SQL. That's perfectly fine to do, and that's really what this is, right? It's the where clause in the context of just limiting a single relation, though not necessarily using it to join 2 relations or something like that. So we denote this with sigma, and we're going to follow sigma with a condition. Now, when there isn't, like when we're abstracting it like this, we don't actually have a condition yet, that's where the C comes into play. The C represents what will be the condition. I'm going to show you an example in a moment that actually has the conditions. So I just want to explain what you're looking at there. So remember here, a selection is choosing which rows the query will return. So here is, again, a example. So we have our relation, which is, we have Star Wars, Galaxy Quest, and Wayne's World here. Again, it's our movies. Now notice we're not limiting attributes. In my results here, I have all the same attributes, but we're limiting rows. So the first one here, I have length is greater than 100, right? So a length greater than 100 now means that when we look at the top full relation here, we can see that only Wayne's World has a length less than 100, right? So I guess less than or equal to, because the query is looking for greater than, but there's no 100, so we're good. So Wayne's World is going to fall away, right? And it does. So using this selection, this is what we get. And notice here that the syntax is that we have the selection, and then we have the criteria, and then we have the relation in parentheses, right? So that's what we're looking at. And now we have a second one below where we add a second criteria. So we have length is greater than 100 and studio name is equal to Fox. So you can look at the original here and you can say, okay, well, let's take it one at a time. Length is greater than 100. So again, Wayne's World goes away. And remember your Boolean logic here with and or and that kind of stuff. Studio name equals Fox. So not that it mattered because Wayne's World wasn't created at Fox, but if it was, Wayne's World would not be part of this result, right? Because it's not or, it's and. So both of these things have to be true, and Wayne's World is not longer than 100 minutes. So even if Wayne's World had a studio name of Fox, which it does not, but even if it did, it would not be returned in this second query, right? That's an important differentiation with and or. So in this case, there's only one that's returned from Fox and one that also has a length of greater than 100, and that is Star Wars, right? So that returns the correct movie there. So that is, now that we've gone through those, that was whittling it down, right? That was taking a relation and looking at one dimension or the other, the attributes of the tuples, and removing. Now we're going to do the opposite. Now we're going to look at how do we add two relations or whatever. How do we take separate relations and bring them together to create a new relation, right? How do we combine? So that's our next step. And the first thing we're going to look at is just kind of the generic product, which is a multiplier, right? We're going to look at the Cartesian product. We're going to take two sets, let's say R and S, and we're going to get the product of them, the combination of the two, which is literally going to be R times S. And this is one of those things that's probably easiest to show it, so we're just going to jump in. The one thing I want to point out before we do, though, is if this is different from when we were talking about just like the set logic, if an attribute exists in both R and S, meaning let's use a concrete example. I have a user relation and I have an email relation. The user relation has my first name and last name, and the email relation has my email address and my user ID. And I forgot to say that my user table, my user relation, also has a user ID. So user has user ID, first name and last name. Email has, let's say it is email ID too, because that makes sense. Although email is unique, so let's leave that off. Email has user ID and email. Both of the relations have user ID, right? So that is an example here where when we return this result, it will contain an attribute for both of them. And if they were both called user ID the same way, instead of one just being called, say, like ID and the other one being called user ID, then they would be noted with their relation name dot user ID. So it would be user dot user ID and email dot user ID. Since we're calling these R and S, it's R, and the attribute that they will share is B. It's R dot B and S dot B. Let's take a look at this. So this, by the way, is starting off with two very small relations. So we have relation R just has two attributes A and B with two tuples, right? Relation S has three attributes. There's a repeat here. There's B again, and then C and D, and there is three tuples. Now, what you look at, like when you do this, it's actually a multiplier, right? Like think back to like, you're multiplying like, 5 times 15 or something, and you first take the 5 and you multiply it by both, right? And if there was something in tens place in the denominator, you would then repeat and do that again. It's the same thing here. So I'm going to take my first tuple in R, and I'm going to come down and combine it with the first tuple of S for the result. So the first tuple in the result is the combination of those first two tuples. So I have A and RB from R, and SB, C, and D from S. And you can see that the 1 and 2 came from R, and the 2, 5, and 6 came from S. Then I took the same first relation in R, tuple in R, and I combined it with the second tuple in S. So now we have 1, 2, 4, 7, and 8. Then we repeat for the third tuple in S with the first tuple in R. So 1, 2, 9, 10, and 11. Now we move on to the second tuple in R, and we repeat for all three tuples in S, right? So it's literally a multiplication. Now, for those of you who may have touched SQL in the past, what this is analogous to is selecting from multiple tables, but without any condition or constraint or join at all. And if you've ever done this and your tables were, say, larger than these, you probably remember that this can be a problem. So, this kind of query can slow things down immensely because, imagine that this is no longer 2 and 3 rows. Imagine that it's like 150,000 and a million. Multiply that out, you get the idea. That's going to be producing a really big result set. Now, mind you also, you might have a lot more attributes than we do here. We only have 2 and 3, right? So I think you can see that this can get out of hand rather quickly, which is why usually there is something called a join. So now that we have just the basic multiplication out of the way, let's talk about how we can get the product of two relations, but in a way that we will match them in some way. Remember, I gave the example before of my user table and my email table. So a useful way to get the email obviously would be by user. So let's say that you want to query me because I logged into the system and I'm going to my profile page and you want to display my email address, right? So you're going to get my user ID because that's probably what you have in memory from having me logged in. And you're going to query the user table to get my name. And then you're going to take that user ID and use that as the join to query the email table as well. And that's the idea here, right? Is that we're going to say, okay, well, that user ID is the same in both places. It's the same in the user table and it's the same in the email table. So I can join these two things and only return the relations where those two things match. I don't get that multiplication factor now, right? I don't just aimlessly get all these rows because I'm multiplying two relations. I'm only returning now the tuples that match, and that's an important thing. So we denote this like you see here with the R and the join S, all right? And this is going to force pairing of tuples on a specific condition. So let's look at an example. So here we have those same two relations R and S, but this time we're going to have them joined on their common attribute B. Now, we haven't gotten into specifying. We're going to talk more about that with data. When we're talking about a natural join here, we're literally just saying that if there is attributes that exist in both, they will be used. And if there was multiple attributes, we would use multiple. I'll show you that in a moment. But for right now, we're just going to stick with these two, which had one overlapping attribute, which was B. So in this case, we're only now going to return tuples that have overlap in B. So let's look at it. So A has 1 and 2. Now our first tuple that we are looking at in S also has a 2 in B. So that's a winner, right? So our first row in our result set at the bottom is 1, 2, 5, and 6. Notice now that there's no longer the repeat on B as well. And then we're going to look at 1, 2, and the second row, right? But in this case, there's no 2 in B, so there's nothing to join. And then we look at the last tuple in S, and again, it has a 9 in B and not a 2, so that doesn't match. Then we jump down to the 3-4 tuple in R, and the 3-4 tuple does not match the 2 in B because there's a 4 in B, but it does match the second tuple. So the second tuple in R and the second tuple in S both have a 4 in B, which means that we can join them. So we also bring down the 3, 4, 7, 8. And the last tuple in S does not have a 4 in B, so that one is not joined. So you can see now we've significantly whittled down the result set, right? Before we had 6 results because it was a multiplication of the 2 by the 3 tuples, and now we just have 2 that represent things that we care about, right? So this is an important concept in relational algebra, is this idea that we're going to join sets, right? We're going to join our relations. Now, we can also use natural joins in other circumstances, such as ones where like a tuple has, you have multiple tuples that match, as I mentioned before, in both relations. Or there could be a situation where more than one attribute are in common, right? So let's look at U and V here. So U has 3 tuples and 3 attributes. V has also 3 tuples and 3 attributes. They both have B and C though now. So before we only had B in common, now we have 2 in common. So let's look at how this plays out. So the first tuple in U is 1, 2, and 3. So 2 and 3 are what we care about for B and C. So we come down to relation V, and we can see that the very first row does in fact have 2 and 3, but so does the second. So we can kind of just speed this up a little and see that we're going to bring down those first 2 right there in the result set are those 2, right? So we have 1 and 2, which are A and B, and then 3 for both, which is C, and then we bring over D from relation V for those 2 tuples that matched. Now the next one is 6, 7, 8 up top, so B and C is what we care about. Interestingly here, 7 and 8 is now the same for both, so for both the next 2 tuples. And if we go down to V, we can see that the first 2 tuples don't match B and C, but the third one does. So we're actually going to have one row of the third relation, or the third tuple in V, for both of the last 2 in U, and that's what you see down here. So you have 6 and 9 for A coming down from those 2 rows, and 10 in D for both the last tuple for both, right, of V. So that is another example of a natural join, this time using 2 attributes that match up. Now this is all great if we're just matching with attributes that happen to be the same, but it's not allowing us to do anything interesting like add a condition. So we talked about before just like getting movies where, you know, the length was more than 100 or something, but why couldn't we also then use those same kind of conditions on our joins? Why can't we say something like, you know, instead of just putting together my username and email relations that I mentioned before, why not be able to do that only for the one that matches my particular user record, right? The way we've just looked at this with a natural join, we can put them together on the user ID, but we're going to get back that relation that represents all of the matches. So if every user has a matching tuple in email, let's just pretend that there's only one email address per user, which is probably a bad assumption. There's probably more than one, but let's assume for a second that there's only one, and you have 100 users and you have 100 email addresses. what we've saved ourselves is having 10,000 results if we had just done a Cartesian product, right? Because we just would have multiplied it. However, what we will have is on a natural join, we'll still have 100 return tuples in our returned relation. And maybe all we want is the one for the logged in person, right? So that now is why we want to use conditions, and this is why we're going to use a theta join. This is going to allow us to do that. So in this case, we're going to denote it just like we were doing before with the two relations and the join operation there, but we're going to have the condition as a subscript. Now that condition, just like we did before, we're going to have it replaced with the actual condition that we use. Now usually the condition is denoted with theta, but I just want to point out that we don't actually use theta in this, like in these things, and neither does the book. So I'm just being thorough and kind of pointing that out. But this is what you're actually going to see. So let's just work through an example here. So given these two relations, we have relation U and relation V again. Again, three tuples with three attributes each. If we have a join on these for U and V, but we put a condition in there that A is less than D, let's look at the result. So we go to A and we say, okay, for the first tuple, A is a 1. Okay, well that's promising. So let's look at V, and we can see that every row, every tuple in V is in fact less than 1. So that means the first three tuples of this result set are in fact R1, 2, and 3 from the first tuple of relation U, and it's matched up with each of the three tuples in relation V, because that was our condition, and A is less than D every time. So you can see that D is brought across. Both B and C are in both, so they also now get the U dot B and the U dot C and the V dot B and the V dot C. And that is how we determined those first three. Now the next two, right, so let's go to the second tuple in relation U. We're looking again for A is less than D, so 6 is A. And if we look at D in V, we can see that only 10 is greater than V. So only the last tuple there is going to work. And in fact, that's the case. So we have 6, 7, 8, and then 7, 8, 10, which matches. And then we look at the last one, A is 9. Again, 9 is less than 10, so that works for the A is less than D. So that last tuple in V is paired up with the last tuple in U to be the last tuple in our result set here. Now the last one here, the second example, is the same with A is less than D, but then we also say, and U dot B is not equal to V dot B. In other words, the B attribute in both of these have to be different. So just like before, we're using an and, so now both of these conditions have to be true. And the only one that works for is that one tuple with 1, 2, and 3 from relation U and 7, 8, and 10 from relation V. Because if we look at B in both of them, B is a 2 in the top tuple of the first one, and it's a 7 in the last tuple of V. And the first condition does still apply, where A is 1 and D is 10, so A is in fact still less than 10. So this now allows us to be strategic when we're trying to combine, again, that's what we were doing here, to combine our relations and give us a new relation, right? I really like that example with the user and the email. It's also a very practical one that kind of comes up all the time. And we'll look more into that when we start building out SQL. But that really kind of sums it up, right? You don't just necessarily want to create these massive relations in memory that are the result sets of these combinations. You want to only get to that data that you really care about, which in the case of the email address is my email address for my profile. You don't have to return all of them, just mine, right? So now that we've gotten through all of those pieces, let's actually start building some queries. Now we haven't talked about the renaming piece, and that's okay. We're gonna touch on that after this. But first, let's try to like tie these pieces together and actually create a relational algebra query. This is analogous to creating a SQL query. It's just, again, this is the underpinnings that we're actually building here. So let's solve this statement. What are the titles and years of movies made by Fox that are at least 100 minutes long? So let's look at this statement and break it up into logical pieces. So notice here, what are the titles and years? So those, right, here we're talking about attributes. We're saying in our result set, we're going to be using projection, right? We're going to be saying we want to limit the result set to just titles and years. Those are the only columns that we want. Of movies means we're talking about the relation movies, right? Now, the made by Fox that are at least 100 minutes long, this was our selection criteria, right? This is where we decided, basically what our where clause was, that we were going to see that a particular attribute lined up to Fox and that another attribute had at least a 100-minute long movie time. So now that we've kind of logically broken that apart, let's look at, in relational algebra, how we'd actually work through the individual pieces. So in order to accomplish this, we can kind of use the bits and pieces that we've already done, and even our set logic, because we're going to have an intersection here. But let's actually do it step by step. So one thing we could do is, because these two things were an intersection, it's an and, we could run the two selections separately, right? So we could do a selection on movies for tuples that have a length of greater than or equal to 100. We could then run a separate selection on movies for tuples that have a studio name equal to Fox. Then we could take the intersection of those two result sets, meaning where they overlap, because remember this was an and that's all we care about. And then we're going to take that result and we can use projection to only return those title and year attributes that we cared about. Let's look at this another way, a visual way. Now this was in the book, but I color-coded kind of the pieces, and I also added them to the top here so we can see the things as they break up into pieces in relational algebra. So part one was that query to select everything from movies where the length was 100, right? The second one was to select everything from movies where the studio name was Fox. Now, the number three is that's our intersection for those two. And then the last one here is we're going to actually be using projection to only return the attributes title and year. So what you see down there, and I apologize, it got moved over onto a second line. It didn't look like that before I put it into this mode, but I'll try to clean that up for when I put the slides up. What we're seeing here is, an entire algebraic statement for relational algebra that represents a query. Now we haven't actually seen the select. What this would actually read out in actual SQL would be select title in year from movies where length is greater than or equal to 100 and studio name equals Fox. That's what an actual SQL statement would look like, that you would create, that would get translated into this relational algebra. You can also make this a little bit more concise by saying the projection, title, and year, and then you can do the selection of length greater than or equal to 100, use an AND operator instead of the intersection there, and studio name equals Fox, and then you can, because they're both being done off of movies, you can do it like that, where you just have movies once. So that's just a little bit more concise, same exact thing. The last piece of this now is renaming. So as we saw before, especially when we're doing joins, you can run into a situation where you had you had two sets, you had R and S, and they both had an attribute B, and now you got R.B and S.B. You can rename, and what this looks like in SQL is, again, I think I mentioned this in the beginning, is if you had select that, say you wanted to select that user ID we were talking about before. So user ID could be in either the user relation, or it could be an email, right? So if I wanted to know which one I was getting back, I would have to say select, say, email.userid from blah, 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 blah. But what I can do instead is I can say select email.userid as call it like e-user ID or something like that, where it differentiates it, but it gives it a new name. And then you can reference in your SQL after that, you can reference that attribute as that new name. So that's what we're doing here. And you can also rename relations this way too. So to do this, we're using the symbol P here. And the S in this case is the first set. So this is going to be the new name of the set. So we're going to, in this case, we'd be starting with a relation R, which is at the end, and at the end it would be called S. All right, so the first set name there is the resulting relation. Then after that come the attribute names. Now, they're always read from left to right. So your first attribute, second attribute, third attribute, etc. So if you want to change the attribute names here, you can do that. You do not have to. We have an example of that down below. But this is how you can change both the relation name. So in this case, we're changing it from R to S, and the attribute names. And here you don't list what they were, you just list what they were what they're going to be. The fact that they're in order is how it knows which ones it's replacing, right? So your first attribute is going to be changed to whatever you put in that first A1 place. So I mentioned here you don't have to rename the attributes, and that's at the bottom. So that's simply the rename of S to R. So here is an example of one that we had earlier where we had sets R and set S, and this is the one where we had the one where we were just joining on B. So we had R.B and S.B. Now what we're doing is we're renaming S.B to X. So once that's done, you don't even have to worry about R.B because there's no longer two of the same thing, so it just reverts to being B. You don't even have to worry about the fact that it was R.B before. It was only R.B because there was two of them, and if you rename one of them, then there's no longer two, right? So in this case, now we would end up with A, B, X, C, and D. And that's because, as you can see there, we changed it to X as the first attribute of R, right? So, I'm sorry, of S, I apologize. And notice here, because we're not changing the relation name, it stayed S, right? So we're changing S to S, and that does come across. The attributes, again, you only need to include those if you do intend on changing the attributes, and then remember that they're done in order. So in relation S, B was the first attribute, and we're changing it to X. So just like all my other slides, by the way, is a habit I have from my in-person classes, and obviously you're not in front of me to, to ask questions, but please do ask them in the forum. So that is what they are there for. I check them frequently, and I do invite conversation because I guarantee if it's a question you have, there is a very good chance that somebody else in the class has it too. And it would be really good to get some conversation going there. So see you all soon, and have a good day.